So we're going to look at some periodic trends. We're going to look at size of atoms and effective nuclear charge, and then we'll go on to look at some other things. So first of all, we have to talk about how are we going to define atomic size? Because do you remember that picture of the balloons, the kind of balloon-looking orbitals? And we said, well, an atom is roughly spherical because you put all these orbitals together and you get this spherical shape. But it doesn't have a hard surface. We draw them like this as spheres. They look like ping pong balls or something. But they don't have a solid surface. There's the orbitals are this region of probability. So where do we draw the line? What do we call the size of the atom? There's different ways of measuring that. We can talk about a non-bonding atomic radius. It's also called the van der Waals radius. And this is half the distance between adjacent nuclei in the atomic solid. So here's an illustration of solid krypton. And you can identify where the nuclei are. And so we're going to say, well, from one nucleus to another nucleus, that's going to be 2 times the radius of a krypton atom. So we'll take this distance, divide it by 2, and we're going to call that the radius of the atom. That's one way. Another way to look at it is the bonding atomic radius, also called a covalent radius. So in like a molecule of bromine, where the 2 bromine atoms are bonded together. Then again, we're looking at the distance between the nuclei, and we're going to call the radius half the distance between those 2 nuclei. This is going to be smaller than if we looked at a van der Waals radius or a non-bonding radius, because that bond pulls the nuclei together. Which one you look at depends on what kind of stuff you're interested in. Okay? So I just want you to know that different ways of defining the radius exist. We're going to talk about atomic radius in a more general way as an average based on different compounds and elements in their different forms as sort of an average general term. This is going to be smaller than the van der Waals radius because it does include some bonding things in there. So if we've got atomic radii, we can approximate a bond length by just adding the atomic radii together. And this would be for covalent bonds. So if we look at the trend in atomic radius, we see that as you go down in a group, the atomic radius increases. So let's see. Let's look at, here's lithium. What group in the periodic table is lithium in? It's in group 1. So here's lithium, and here's sodium, and potassium, and rubidium, and cesium. So, and hydrogen's way down here. So as we go from the top of the period to the bottom, the atomic radius increases. So this is the radius versus atomic number. So we see that as we go down the period, the atomic radius increases. This is reasonable, okay, because, well, cesium has a lot more protons, a lot more electrons. It should be bigger, right? The biggest factor, though, is that N, the principal quantum number of the valence shell, is increasing. So hydrogen is in period 1, lithium's in period 2, 3, 4, 5, 6. Cesium's valence electrons are in the 6th energy level. That's farther from the nucleus. Lithium's valence electrons are in the 2nd level. That's closer. So cesium is larger. If we look at going across a period, well, let's just, going across a period would be something like this from lithium going over to neon. Neon is at the far right side of period 2. Lithium's at the far left side of period 2. We can see from this graph that the radius goes down as you go across the period. This does not make sense intuitively. Neon has a molar mass of 20 grams, and lithium's only what? 6? Yeah, 6.9. if you had to guess, a reasonable person would guess that neon's bigger. It weighs more. Why isn't it bigger? But we see this trend repeated over and over with each of these periods. As you go across, it gets smaller. What's going on with that? Here are some actual numbers. So we see here's lithium, radius 152, 112, 85, 77, 70, 73, 72, 70. So there's a little glitch here, but overall they're getting smaller. And these trends are trends. They're not absolute. There are exceptions, like this one with nitrogen here, but in general, as you go across. Well, let's think about where are the valence electrons going? When we learn to do electron configurations from the periodic table, we think about, okay, here's lithium and it's got a valence electron. It's 2s1, and we add another electron, 2s2, add another electron. This is in 2p1, and we're adding electrons, right? What level are we adding them to? The same level, right? As we go across a period, we're adding electrons to the same energy level. So energy level 2 is closer to the nucleus than energy level 3. But as you add electrons, it's going into the same energy level. So then thinking about that, we might say, well, then they should all be the same size, right? If you think of it in terms of the Bohr model, where you've got planets orbiting the sun, electrons orbiting the nucleus, all we're doing is we're adding more planets to the same orbit. Why is it getting smaller? Well, it has to do with shielding. Okay, we talked about shielding last week. We've got this simultaneous attraction for the electrons to the nucleus and the repulsion from the other electrons. And so the outer electrons get shielded from the nucleus by the core electrons. So those outer electrons, the valence electrons, do not experience the full strength of that nuclear charge. Here's our friend lithium again. So there's the nucleus for lithium, positive 3 because there's 3 protons. Here are our core electrons, 1s2, and they're in this s sublevel, this spherical region. The valence electron is in the second energy level, which on average is farther away. And so when this electron looks at the nucleus, this +3 charge is shielded by those 2 electrons, so the effective nuclear charge is only +1. That means that this electron does not experience the same charge attraction that the other 2 do. That make sense? We can quantify that and call it the effective nuclear charge. That's the net charge experienced by an electron. So the effective nuclear charge is the actual nuclear charge, which is the same as the atomic number, the number of protons, and subtracting s, that's the number of core electrons that are shielding. Okay. Valence electrons do contribute to shielding, but it's really small and we're just going to ignore it. So if we look at nitrogen, what is the effective nuclear charge for nitrogen? So the actual nuclear charge is 7, right? So it's got +7. And then how many core electrons does nitrogen have? Well, it's easier to answer how many valence electrons does nitrogen have. 5. It's got a total of 7 electrons. 5 of them are valence electrons. The rest are core. So there's 2 core electrons. So 7 minus 2 core electrons is an effective nuclear charge of +5. Okay. What about argon? What's the effective nuclear charge for argon? Well, argon has 18 total electrons, right? And how many valence electrons? 8. So the rest are core electrons, so 10. And so it has an effective nuclear charge of +8. That make sense? You take the actual atomic charge and you subtract the number of core electrons. That's your effective nuclear charge.
Do they have any net electron charges or net charges that are negative, or is it most always?
No, you can't have an effective nuclear charge that's negative. You can't even have one that's zero, actually. So here's quantum mechanics explaining the trend. As we go down, I kind of jumped ahead. As we go down, the valence electrons are going into a higher principal quantum level, right? So that results in larger orbitals and larger atomic radii. As we're going across a period, the effective nuclear charge increases while the principal level remains the same. So this gives us a stronger attraction between the valence electrons and the nucleus and pulls them in tighter. So we just said that the effective nuclear charge for nitrogen was +5. We did argon, but let's compare neon instead, because neon's in the same period as nitrogen. What's the effective nuclear charge for neon? Well, what's the atomic number? Is 10. So that's the actual charge on the nucleus, and how many core electrons does neon have? 2. So neon has an effective nuclear charge of +8. So the energy is proportional to Q1, Q2 over R. The charge of the electron and the charge of the nucleus divided by the distance between them. Well, the charge on the electron isn't changing, but the effective charge on the nucleus is changing. Here we've got +8 instead of +5. So that pulls things in. Any questions? You need to be able to remember the trend in atomic radii, that as you go across a period from left to right, the atoms get smaller. I find it easiest to remember why, because then when I forget the direction, I can think it out. The transition metals are a little bit squirrely, as they are for everything we look at. So with those transition metals, in the group, as we're going down, they do increase in size, just like the main group elements do. But when we go across a period for the transition metals, the radii are roughly the same size. And the reason for that is that the valence shell is NS2. As we're filling in those D block electrons, those are not valence electrons. The S electrons are. And so all of these guys have mostly the same number of valence electrons. And so we're not adding valence electrons, we're adding core electrons as we think about adding protons, and so the effective nuclear charge is not changing. So if we think about, let's think about something familiar. Let's think about iron. So iron, Fe is, what am I doing? I don't even know what I'm doing. Let's look at iron and zinc. They're both in period 4. And so as they're going across that D block, we're filling the 3D sublevel. How many protons does iron have in its nucleus? 26. And how about zinc? 30. Okay, so how many core electrons does iron have? How many valence electrons does iron have? Iron, yes, got 2. So iron is going to be argon plus 4s2, and then we're filling in 3d, 1, 2, 3, 4, 5, what, 6? 3d6. So the valence electrons is the 4s2. Everything else is core electrons. So if it's got 26 electrons and 2 are valence, that means that 24 of them are core electrons. So our effective nuclear charge is +2. So for zinc, zinc is argon, 4s2, 3d10. How many valence electrons? Still 2. So how many core electrons does zinc have? 28. Same effective nuclear charge. The electrons are in the same sublevels. The effective nuclear charge is the same. The radius of each atom is roughly the same. Does that make sense? So let's go back. That's not back. Let's go back to this graph. And what we see here in the green, here's the period 4 transition elements. Now, there are some variations. As we go here, there's a bit of a decrease, but then these guys, this is almost flat here. And period 5, this is roughly flat compared to the differences we see across the main group elements. That's because the effective nuclear charge is the same. We cannot predict absolutely just based on these trends, but we can predict in general. Okay, any questions? Okay, so what might I ask you to do on an exam? I might ask you a question like this. On the basis of periodic trends, choose the larger atom in each pair if possible. Sometimes you can't, just on periodic trends, but let's look at these. So what we have to do is we have to find these on the periodic table. So tin and iodine. Okay, so they are in the same period. So there's tin, and over a couple of boxes is iodine. So I'm just kind of drawing a little piece of the periodic table to show how they're related to each other. So we're looking at a period, we're going across a period from tin to iodine. Do they get bigger or smaller? They get smaller because the effective nuclear charge increases and pulls the electrons in tighter. So which one's larger? The tin. Okay? Germanium or polonium. You don't have to know the names of those. You just need to know the symbols and be able to find them on the periodic table. So these guys, this is a little funkier. So there's germanium. And then going down here is something else we don't care about. And down here is polonium. That's not a very good O. So there's two things going on here. We're going from left to right. We're also going from top to bottom. So we look at those two changes separately. Here we were just looking across, but now we're looking across and down. So when we go across, does it get smaller or larger? Smaller. So this one's going to be, so from that we would predict the polonium's smaller. But as we're going down, what happens? They get bigger. So those two trends contradict each other, don't they? So I would have I would accept two answers for this. I would accept can't tell. I would also accept, or we could say that we predict that polonium's going to be bigger. So choose the larger one, or PO is bigger.
You can't tell from the valence electron.
So why might I say that polonium is bigger? Usually this downward trend where we're adding to larger principal quantum numbers, that has more effect than going across and getting a little more effective nuclear charge. Okay? Any questions? And then CR or W, that almost looks like crow. I'm not distractible at all. CR and W, chromium and tungsten. There's chromium and tungsten. Okay, so they're in the same period. So here's chromium and here's tungsten. Which one's bigger? Tungsten. Tungsten's bigger because as you go down a group, atoms get larger. Any questions?